So we are ready to rock with the second part of the Detector full simulation tutorial, where Chris will give us an introduction how one can integrate detectors into the fun4all framework and do detector simulations with this framework. Chris, please.
Yeah. Okay. So just as an introduction, we have it on the Indigo page. So that's the link to the tutorials where you can, cut and paste the commands from later on, rather than, typing these lengthy things. And I hope you all have, you'll all be able to run something either with an RCF account, JLab account, or with the VirtualBox in Singularity. All right, let's start. Come on. As soon as my screen unfreezes. At least Bill Gates gave $100 million to the coronavirus research, so I guess we'll finance this here with that. Hang on, I just stopped sharing. Let me just fix this here. Sorry about that. All right, can you guys hear me?
Yes.
Okay, sorry about that. It's an old laptop, so. Okay, so this is the introduction into fun4all. When my daughter saw this, she said, "Oh yeah, that was a cool place. We used to go there when I was small." So yeah, so the name is coming from Long Island's own, reasonable priced fun park, and that's basically what we're doing. We build our stuff and we have fun with it. Okay, so the structure. So I'm going to give a short introduction into fun4all, and then I go right into Yaroslav's luminosity monitor, implementing it with least modification on his side. And then it's going into fun4all, then for real, all the using some of the capabilities it has. There will be an example how to implement a simple detector, in quotes the right way so that you can actually read it out. Then an example about determining momentum resolution of configurable, sorry, it's just a silicon right now, so I left out the TPC. And then an example how to add your detector, so Yaroslav's detector, to a full detector implementation of an EIC detector. Now the usual list of other things you can do with it, where you can get help, and where things are going. So what I assume here is that you have some basic C++ knowledge, that you know what a base class is and what virtual methods are. A basic familiarity with root, so fun4all uses root cling as the command line interpreter, so you have to know what a root macro is, and you should know how to draw histograms from n-tuples. Currently what we do, we support root 5 and root 6, but root 5 is being phased out. We just drag it along as long as it doesn't really interfere with what we're doing. So you can run our software either with an RCF account, or on your laptop, desktop, with getting our Singularity from GitHub. There's an explanation how to do that. There's a script which downloads the stuff, makes local copies. As of recently, we can run on the JLab farm. So if you have a JLab account, you can have a look at this tutorial too. Example JLab that gives you the 5 commands you need to run it on JLab. You should have some familiarity with Git. What's a Git repository? How to use Git clone. And in the future, you definitely want a GitHub account for this. So everything is stored in GitHub here. So a brief history. So the development of fun4all started in 2002. It's been in use by the Phoenix collaboration from 2003 on. We do reconstruction, analysis, embedding, you name it. So it's our workhorse. At that time, it needed to get many subsystems who developed their code independently and without coordination under one umbrella. So this thing is very flexible, and many different pieces of code of people who didn't coordinate. That sounds pretty much like the simulation effort going on with the EIC right now. So it comes from the same, deals with the same kind of problems. The development of it is purely driven by reconstruction analysis needs. There's no real beauty or abstract design considerations in there. Basically, it does what needs to be done. And if you have to change some things, we'll do it. Modularity is absolute key in this concept. Nothing relies on other parts of the components of it, input, output, reconstruction modules. They can be added, modified, and removed without actually having to modify anything else in this universe. Yeah? So that makes changes really, really easy. We added naturally, over the years, we added plenty of functionality. I'm pretty sure we forgot some of them, so they're kind of waiting to be rediscovered. In 2011, we started looking into Géant 4, so we basically added the capability to run Géant 4 inside fun4all. So we have, in the meantime, 8 years of experience with running. Actually, it's 9 years by now. So 9 years of experience, with Géant 4. And in 2015, we basically split it off from Phoenix and then did the usual, what you do when you split off from somewhere, like, oh, let me change all the things I always wanted to do because they were annoying. So lots of cleanup and plenty of modernization in there. So what does it do for us? It reads input files with many different types. It writes output files, again, different types. It has an automatic saving of selected data objects, so you don't have to think how you want to write out your hits. The framework basically does it for you. You don't have to define them. That it basically takes the class you give it and makes it persistent using root. There's something called a node tree. That's our internal storage structure for data objects. It kind of manages that, but again, users can, add nodes, read from anything they want to. It calls the analysis or reconstruction modules in the order in which they were registered in a macro. So, but that means the correct ordering is your responsibility. If you reconstruct the tracks before you reconstruct the hits, you will not get any tracks, and there's no warning about it. So it's your responsibility. The assumption is that the user normally knows best. So, I hate it when a framework basically tells you you can't do certain things, even though you know it's the right thing. So no restriction on that front. It can make snapshots at any state of the reconstruction analysis. So what it does, it basically dumps all the objects on the node tree into a file and can read them back. So you can stop your analysis chain at any time and pick it up from there, as long as you stay within fun4all. And it has an interface into a calibrations database or file-based calibrations. As pointed out, fun4all has been our workhorse for 16 years now. It's running raw data reconstruction, analysis, simulations, embedding. For those of you who don't know, Phoenix is a heavy ion experiment. We've taken, I think, 10, 20 petabytes of data. Biggest data sets were 3 petabytes. We run a regular analysis over older data sets, which are like the biggest ones, 400 terabytes, and we do this within 24 hours. So this thing has seen its share of use, and it's very well debugged. So here's a little picture of the structure. Structure is rather simple. On the upper left in green, that's you, and you just basically talk to the fun4all server on the command line. So the fun4all server in itself then talks to the input managers, basically tell it, okay, I want an event, and then the input manager goes off and fetches an event. We can read DSTs. That's an old name. It's data summary tape, so it's reconstructed output. It can read raw data. In that case, there was PDF file. So for the EIC test beams, Martin's data acquisition system, the RC DAC, writes these files. So you can actually read raw data files from lots of these ERD test beams. It can read generic HepMC files. There's an old standard called Oscar. I'm not sure if that's still being used, but we can read it. It can read the output from EIC smear. So EIC smear can basically read in itself quite a lot of EIC-related Monte Carlo outputs and basically writes it into some output, and we can read that output. So this gives us access to all these EP and EA generators. And then actually has an empty event loop. So if you just want to drive the event loop, you basically just have a dummy input manager. You can combine these things. So you can have multiple input managers. So you can read from multiple sources at the same time if you want to. Very practical for embedding, for example. The next step is then this node tree. Again, it's our global data structure. And what the input managers do, they basically put their data on the node tree, and that's it for them. They have no idea what the output is written out or how the stuff's going to be analyzed. Again, everything is modular, so their job is done, and they don't care about anything else afterwards. On the right side, you find the output managers. So they read from the node tree, and they can write these reconstructed output, our DST, so these root objects. If the input is a raw data file, they can write out a raw data file. So far, we have no real intention to write out raw data for reconstructed data. That just doesn't make any sense. If you have an HepMC formatted input file, you can basically dump this into an output file. And that's basically what these guys do. Then further down under the node tree, you find the reconstruction analysis module. So this is what I said, in the order in which they are registered with a server. It basically runs over the reconstruction modules and tell them to do their thing one after the other. The reconstruction modules can access calibrations. Again, we have a Postgres database backend for calibrations, or it can be file-based. So we can do either or both if you want to. Since root is a bit quirky in terms of histograms, when you create a histogram or you open some file, you create a histogram, and then you close the file, the histograms are gone. I have no idea why they thought that's a good idea. But anyway, so the reconstruction modules, they have they can call a histogram manager, which makes sure that the histograms and untuples and T-trees, whatever you want to write, survives. And you can tell it then at the end to dump these things into root file. That's basically all there is to it. There is no backdoor communication between the different components. Again, modularity. You don't want these backdoor chattering there between modules. And the whole thing is steered by root macros. Coming to the simulations, they are Geant 4 based, so we have no Geant 3 and no virtual Monte Carlo. They are fully integrated in our analysis chain, so technically they are run as a reconstruction module, so just something fun4all calls and lets it do its thing. It's modular in itself, the simulations, it's modular design. All detectors are self-contained, so there is no overlap between detectors. You can add them, you can remove them on the macro level without ever having to change kind of central code. So you can add a new detector, you don't have to change anything of the central code, which, if you have a large group of people modifying things, that's a real advantage of it. This whole thing, the simulations as well, are configured with root macros. We have a few generic detectors you can basically just use, the boxes, cylinders, and cones. You basically tell them what material they are made of and where they are, what rotation they have, and it basically puts them into the world for you. We have a full implementation of an EIC detector based on the S-Phoenix Barbar magnet. These detectors are fully implemented, and they're fairly complex. You'll see an event display later on. Again, as I pointed out, that's been like 8 years of development for Geant 4, so we do have a lot of experience with it, and it does work very well. The EIC implementation has been used for publishing EIC detector concepts, so this is 2 references over here. So it's not, this thing has been used and results have been published. We do have some tutorials down there. There's a link. We'll go over a few tutorials here, but there are some more if you're interested. So now coming to the program flow. So on the left side, you've got fun4all. So on top, you've got the fun4all server. And in yellow, then the node tree, which contains our data object. Sorry. And on the right side, you've got the Geant 4 world. So again, they are totally disconnected. They don't talk to each other. So what fun4all does, it as you saw in the input, it calls an event generator. Typically, can be from an input file, like an HepMC file, can be a single particle generator. We have a few of those. There's the particle gun or some distributions, or we have some D-meson generator. So whatever you want, basically you call the event generator. And what the event generator does in the end is basically just putting particles onto the Geant 4 particle stack, where they come from, so their vertex and their momenta and the particle itself. The module then, which fun4all calls, is called PHG for Rico. So what it has to do, it initializes Geant 4 before the detectors are added. So there's actually a problem when you live in the pure Geant 4 world. The messenger is instantiated after Geant 4 is initialized. So you kind of you have some restrictions there, which are alleviated with that scheme. So we buffer all the parameters and then hand them down to Geant in the correct order. So this is why we actually can do these, adding detectors on the fly. So PHG for Rico, again, as I said, is basically a loop. It calls a interface object for a detector, and this interface object in the end has to provide a construct method. That's the standard Geant 4 method that you basically construct your detector, geometry, material, all that stuff, which then gets put on as a detector into Geant 4, and then it has to provide a stepping action. And the stepping action is called by Geant after every Geant 4 step, and that's basically the place where we extract the hits out of Geant 4. And as you can see, the arrow to the left, we extract those hits and put them onto our node tree that we can later on analyze them or save them in an output. And it's a macro. Every detector is independent from each other, so you can just you just chain up the detectors in your macro. Call one after the other. And pointing out again, generic detectors you can just put there on the macro level. You don't have to write a single line of code for that. Then if you stay within the system, afterwards you basically then call the reconstruction. So the next thing you do is you digitize the hits. If you want to read raw data, basically the raw data come in at that point. So after digitization, you kind of hope that you have, kind of raw data in memory. So then what you do, you tracking, clustering, afterwards jet finding, epsilons, photons, you name it, you do your analysis, and you can, write output files at any point. So this thing is basically a whole chain starting from the event generator up to high-level analysis. Yeah, everything within one. From our experience, breaking this chain is just basically a really bad idea when you have to propagate knowledge and information from one system to another one. You always forget things. It's just it's basically a permanent nightmare. So currently implemented event generator. So what do we actually have now for real as of now? So via the EIC smear interface, EPEA, so they have a Pythia interface. I think it's Pythia 6. Then Pepsi, Django, RapGap, So yeah, these guys over there. Fun4all has its own. We have our own event generators implemented. So Hygiene, that's a heavy ion generator. We have Pythia 6 and Pythia 8. We have Sartre. Jetscape needs a bit of work because it writes HepMC3 files, and that interface to HepMC3 or HepMC3, the API is a bit in flux. So that basically is one, if needed, then we'll get around to it. We had, 2 years ago, there was a version running, so it basically just means implementing the current HepMC3 format, which I hope will settle down. It's a lot better than HepMC2. So we can read generic HepMC2 files. If the generator produces them, we can read them. Oscar, as I said, we have single particle generators. And what we also support, I didn't mention that so far, is we can embed particles into existing events. This is, again, probably more a problem for, our, for collisions with a lot of particles, where, if you'd rather embed single particles into it and run the simulation for the single particle, rather than running the whole, 1,000 particles, which just takes eternity. So you take an existing simulated event and you can put other particles in there. So on the right side, you see, some displays. So, the very powerful heavy ion collision from Hygiene. So we have Sartre, that's up there on the top right. Just to point out the original particles you can see coming in the middle. There's a little red one. So it's two particles going off, but then it hits the hadronic colorimeter and basically makes a huge shower in there. So this is why this thing looks, so dense, while Sartre itself just produces a few particles normally. Then we also use it, Fun4all, for the NASA Space Radiation Lab over here. So you have, 10 GeV gold on a water phantom. So, that's what happens when, an astronaut gets hit by a cosmic ray. And then on the right side, you see it's Pythia 8. Again, it's a provided event generator by Fun4all. And, a 6-layer silicon detector mock-up and a 2 Tesla field. So this is later on for the momentum reconstruction. Or basically, this is what we're going to use. We preserve the full truth information. So anything can be traced back to the input particle later on. So we have evaluators which actually work on jets. So we take a jet apart and see basically where, which Pythia particle this thing came from, which part on there. So we can do that. Okay, how do we distribute this whole thing? So we have an operating system image that's here from RCF. That's the scientific Linux 7 distribution in a singularity container. As of a couple days ago, we also have as a Docker container. The libraries and third-party packages, and we use quite a few of them, is installed in CVMFS, which basically means, they are centrally managed, but you don't have to manage them. So I would take this as a plus. We have a dedicated CVMFS volume for the EIC. So that's CVMFS eic.opensciencegrid.org, where we, put these third-party libraries. The nice thing with the opensciencegrid.org CVMFS volumes is you don't need any keys or so to access those things. So they're world readable, and if you run CVMFS, if you have it running, then you can read these things. You have 2 scripts to set up the environment. The first one is the EIC setup. If If you run bash, then use the .sh. If you have a TC shell or C shell, then use .csh, please, so they're not compatible. In addition, when you build your own detectors, when you build your own code, you need a local installation area, and then you have to source these setup local script, giving you install area as an argument to basically set up your LD library path, the root include path, and your path, so to basically prepend your installation to to the regular path. And the reason for that is the root include path is with root 6 is kind of tricky, so that needs a script. You can't really do this by hand. Okay, now how do you actually build a package? So we use autoconf and automake. It's basically configure to build our code. Sadly, this does put some files into your source area. So you basically check out the, you get the code, and then you run this autogen, and then you find a few files and directories in your source area which don't belong there. So that's a disadvantage. CMake does a better job on that one. Just be careful what you commit. If you say commit everything, then you get a bunch of auto-generated files in your commit. It's not a problem. They get overwritten. It's just doesn't look nice. Each package or directory is built by itself, so we don't have a global installation somewhere where you call one make and it just goes off and builds then 500 packages. So every package is built by itself. The advantage for you is that you only have to build the package you're actually working on. Yeah, so you basically git clone the code, but then you only work within the directory you're actually working on. You only have to build that code. A word of advice, keep your source, build, and install areas separately, but you definitely want to use a common install area. So in green you find the scheme. So you have for one package, source one, you have a source directory. You make a build directory, so you don't build inside the source directory, and then you use source autogen.sh is just a simple script which in the end runs configure. -- prefix, then the installation directory where everything should go, and then you do a make install, and the stuff ends up in your installation directory. Second source you put into a separate area, separate build area for it. Autogen make install. You want one install area only, if possible. If you will see in the examples, I'm using relative paths for the autogen. It's quicker. If you want to use the debugger, you need to use the full path. Otherwise, you can't find this. The debugger can't find the source file. And if you use your install area, then you need to tweak the environment. As I pointed out, you have to call this setup local script. Again, in the examples, we're going to do that. So let's have a look at Yaroslav's luminosity monitor. So the project itself it's a Xeon 4 based simulation, and it uses handmade root T-trees to save the output. So the goal was, just keep the code changes to an absolute minimum. I'm not trying to re-implement this thing using fun4all features. And basically that means using the fun4all G4 our detector implementation as a simple wrapper around Yaroslav's code. I was surprised actually how easy that was in the end. So the changes which were needed was Yaroslav's detectors they inherited from a sensitive detector, and he had his own detector way of organizing the detectors with a base class, so that had to go. And then since the stepping action was different, so it had to be, I had to store physical volumes inside his stepping actions. I had to propagate these root T-trees downstream, because I got rid of this detector base class. And so I basically replaced the detector construction.cxx by, I called this thing G4Lmon detector interface, which is very close to a copy of the detector construction in the end. I dropped the G4 messenger because fun4all doesn't talk G4, at least not this way. I dropped the input reader, so that's what the framework provides. I couldn't really make sense out of the file itself, so I assume it can be replaced by EIC smear interface. So I didn't write a dedicated input input manager for his files. So in the end, it basically boiled down to 20 lines changes in CXX files and 8 in his include. There was some missing declarations somewhere which needed to be added. So basically 20 line changes, and he was good. So let's see how we do this now. So there's the original code is on the left, then the fun4all base code is on the right. So let's start with the first example. I put the cut and paste instructions from the web page into an editor over here because it's easier for me to cut and paste. Yeah. So let's start with an empty world with empty things. So let's make myself an EIC directory. Oh. Wipe this one off. Can you guys still see that?
Yes, I currently see your editor.
Okay. Yeah.
Looks like Emacs.
Emacs, yeah. Emacs is what did they say? It's a complete operating system. It only doesn't have a decent editor. So, okay, let me cut and paste in here. So as I said, first you have to source the EIC setup script. Again, I'm using Bash here. If you use CSH, use the EIC setup.csh. Then I'm cloning Jaroslav's monitor inside fun4all. Make myself a build directory. Go down there. And then I call the autogen. And I'm going to install everything in my home directory in my install. If you want something else, put something else there. Yeah. Oh. What? Okay, I forgot this one. I'm sorry. So let me go to the source directory. So now make a build directory here. Okay, so what this thing basically does, it figures out what operating system you're on, how to call the compiler, all these things, which is kind of work when you try it yourself. So, and then I just run make install. Okay. Okay, since I have now my own package, I have to do the setup local in order to add, the libraries and everything to my paths. It just prints out what the LD library path looks like and the path looks like now. Just in case things don't work, then you can have a look here. So here you see that's my install the library path over here. Okay, now let's go to the macros area. Let's just have a quick look how this macro actually looked like. I say everything is steered by macros. The top is root 6 makes it a bit tricky with the include files. You actually have to include all the include files as of root 6. It's not enough. In root 5 it was enough to just load the libraries. In root 6 it's not. So you have to include all the include files being used. So what do? So first we give us a pointer to the fun4all server. So again, as I said, you talk to it. The fun4all server is the only thing which has an instance here. Yeah, so that's a singleton. It's always the same one you're talking to. And okay, sorry, there's another one. These recocons is basically it's a bag full of parameters. For example, for reproducibility, sometimes, if things look weird, you want to be able to reproduce identically what you did before. So you can actually fix the random number seed here, and that will determine the future sequence of all the seeds, and you can basically run twice and you get identical results. Yeah. Okay, then we have down here the particle gun. So we have a particle gun. What we do, we put a gamma in here and a pi minus because it goes magnetic field. So I just want to see how it goes. That the pi minus actually gets deflected while the gamma goes through. We set it to vertex 0, 0, 0, so just at the center. And this thing in this world is basically backwards. So set it to minus to 1 GV over C in the Z direction, and then we tell fun4all with the register subsystem to actually use this gun, to call this gun. The G4 setup, again, it's PHG4Rico, so we make a new one of this one. We don't want to have a magnetic field around in there right now, so you can put in a solenoidal field or field map, basically in the world. And since it saves time, we don't want to save the geometry. And here's our Yaroslav subsystem. Yeah? So it's in the library, so we basically say, okay, we want a new subsystem and just register it. Yeah? With G4Rico, and then we tell fun4all, okay, register G4Rico. So then we have an input manager. As I pointed out, this is a dummy manager that doesn't do anything. It doesn't put any particles, nothing onto the node tree. It just drives the event loop. You register the input manager with fun4all, and then you just run events. Yeah. So basically here you can see the order in which things are done. First it calls the particle gun, then it calls the G4 simulation, which in itself calls the Yaroslav's module. And that's it. And the input manager, okay, we have it at the end. If you have it at the beginning, it's fine. Yeah. So let's see how this looks like. This. Yeah. One thing, the argument, as you can see, is always in these macros is always the number of events. Yeah? If I say -1, it doesn't run any events. It basically just it fires up the display afterwards. Yeah? So you don't want to run any events for this. Here you can see this is Yaroslav's output, so it opens these almond.root from Yaroslav. There's a root macro which basically turns on the display capabilities or defines them, and then you can call methods from within there. Okay. Now this is Yaroslav's luminosity monitor. Yeah? And what you can see, so basically I can pop up the G4 interface. You lose the root interface at that point. So basically this thing takes over. So let's put an event in here. Yeah? So there is a little messenger from fun4all to G4. Right now the only thing you can do, it basically calls this run method, so that you can run events. If we need more, then it's no problem to add those. And then we wait a while, and there we are. You see the photon goes straight through, hits something in Yaroslav's luminosity module, and the pi gets deflected. In here is a magnetic field, the dipole field, which then deflects the pi minus. Yeah. You can run another one if you want to. Okay, there we are. Pion goes again and to the side, and the photon hits against something. Okay. So let's go back to the presentation. Oh yeah, okay. So these are the cut and paste commands I just executed. So now the question is, why should Yaroslav actually do that? So what's in for him? Yeah, okay, he gets access to all implemented generators, so that's nice. He doesn't have to write decoders for every single one of them. And he can keep using everything he developed downstream. So because as you saw, we basically open his root file. His stuff puts into the root file whatever he puts in there. So he doesn't have to change. He doesn't have to change his downstream analysis. So because there's no changes to what he's actually writing out. And yeah, there's less code to maintain. I mean, it's the G4 manager, the messenger, and the input generator. But I mean, seriously, is that a good reason? If somebody gives me this and tells me I have to change my code, I'm basically would say, like that doesn't sound very reasonable. But what else is in there? So he can actually start playing with the big hits. Because as I pointed out, our detectors are added on the macro level. I can basically take the macro you just saw. We'll go. Example 3 shows then how this is really done. I can take his subsystem and just add it together with our EIC detector implementation. So, I can add his detector to other detectors easily without having to recompile anything. Naturally, there's some fine print. As I pointed out, the stepping action is the one which puts data onto the node tree. He uses his own stepping action, so it doesn't put any objects on our node tree. So it just puts it into his root file. And with that, this doesn't include the detector into any analysis chain, because you can't even get to the hits. As of now, if you look at the detector, you see this big white box. That's his vacuum system. It basically totally overlaps with the EIC detector. So yes, there currently there are overlaps, and they need to be dealt with. And our world is filled with air. So our technicians would be very unhappy if we would evacuate the experimental hall. So in order to get photons and pions out there, you would have to really add a beam pipe, vacuum system. Okay, so now let's see. Now let's use fun4all for real. Coming back to Yaroslav, so this is basically the program flow in his example, in his code as is right now. So you have the fun4all server. It makes the event generator, calls phg4reco, which calls his detector. It constructs it, and the stepping action writes its output file. So that's basically the program flow in the current example. But okay, this is kind of not what you want in the long run. In the long run, you want this kind of stuff where you can actually combine multiple detectors and analyze what comes out of them. Coming back to some internals, you need to know what Geon does, or Geon4 does. It basically propagates particles one step at a time. That's called these Geon4 steps. The step size is determined by physics processes which are associated with the current particle or when a boundary is crossed. And it basically throws the dice and just decides then what will end this step. After each step, the user stepping action is called, basically with a pointer to the current volume. And with that step, you have access to the full information of that particle. You've got the energy loss, particle momentum at the beginning, at the end of the step. So this is basically what gets handed to you in your stepping action. Okay, so what do we do? I talk about Geon4 hits and not Geon4 steps. So what we do by default, again, we are flexible. We have implementations where this is different. But by default, in our stepping method, we basically just integrate the energy loss in every volume, and then we just store the entry and exit coordinates and the time. We can store detector-specific information For example, for colorimeters, for scintillators, you want the ionization energy or the light output. For the absorber, you really don't care. You won't even get any light output. For tracking detectors like a TPC or the silicon, you want the momentum at the exit point to basically see how well you reconstruct that. So every detector has specific information you want to save. Our hit structure is flexible enough; we can do that. And what we also do, we keep the ancestry of these hits. So this provides us then with a means to trace everything back from looking at the jet and tracing it back to the input particle. Just to reduce size, imagine that this truth information is big, because especially for showers, you have you store, in principle you have tens of thousands of particles in there. We do not store any particles which don't leave any hit in the detector, and which are not in the ancestry of a particle which leaves a trace in the detector. So basically, the idea is particles which are undetectable, we don't store them. And again, detectable means it leaves energy in our detector, the particle or its daughter somewhere. Now a little section about the node tree I've been talking about a lot. If you want to analyze that, you have to have some basic idea what this thing is. So on the right, we have three types of nodes. That's the composite node. These things are basically, it's like a directory structure. You have the composite nodes are directories, and then the data nodes and I/O data nodes, they are files, or objects in this case. A composite node can contain other composite nodes or data nodes. The difference between a data node and an I/O data node is that the I/O data nodes can be written out into a root file, which basically means they have to inherit from the object. A data node doesn't. So in principle, on the node tree, you can put any object on the node tree. It's not just, they don't have to inherit from the object. They don't have to be able to, be written out. So if you have something a subsequent module needs to access, you can put it on the node tree. A little write-up. So basically what you need to know is, again, it's a centerpiece, but you don't really see it. It is not a root T-tree. That's very important. A root T-tree has a bunch of restrictions we don't want to put onto our, basically we don't want to have on our node tree. What's being saved onto the output file is the composite nodes and the I/O data nodes. So basically the directory structure plus the data nodes. The DST in itself now, this is physically it contains root T trees. So the node structure, technically is saved in the branch names, and the I/O data nodes, there are some limitations from root. In root 5, it was basically anything containing boost wasn't possible in root 5. We have to see how far root 6 can take us there. So we are still working on that, see what possibilities are there. But basically, the I/O data nodes, the objects in there, they have to, live with root's limitations. What we do in the file, when you open a file, you can open a file with the G browser if you want to. We save two root trees in every file, one which contains the event-wise information and one which contains the run-wise information. And our input managers, they open these files, then they reconstruct from the stored, from the branch names, they reconstruct the node tree, the directory structure, and then they put the objects back into the nodes. And the output managers have the capability, we can basically give them a selection of these data nodes. So we don't have to save everything. The default is saving everything. If you say, I only want, whatever the hits in the TPC, you tell it to only save those things. Fun4all can manage multiple independent node trees if you want to. For embedding, it's very practical. You have one node tree containing the background event, one node tree containing the foreground event, and then the third one is where you mix things. Yeah. Okay, having a look at the node tree in itself, that's now the default you see. So what fun4all does for you, it basically creates this tree, gives it a top node, and it basically gives you a top node. That's the default. And then it creates a DST and run nodes. Again, the DST contains the event-wise information. The run contains the run-wise information. Again, there are some quirks from root, which we just have to live with. For example, that root T-trees only give you, when you ask for a given, in quotes, event, it basically gives you an entry back. Now, if you start a root tree and you only add objects after the first, or maybe after the first event, and you ask for the first event, it will basically mix the first and the second event. So what we have to make sure, and our code does that, is that after you start running, you cannot add anything under the DST composite node to prevent event mixing inside your root file. You can add your code, you can add other composite nodes if you want to, and there you can actually do what you want. So what we have is that we call it the par node. So this is where complicated geometry objects reside, stuff we don't want on our DST, or we can't save on our DST. So for example, the field map is hanging there. You can see it's a PH data node, so that cannot be written out. And our beam pipe has its geometry. So this is the place for more complicated objects, which are easy to access in your code, and you don't care if they're written out. If you print out the node tree, this will become apparent later on when you want to access the objects on the node tree. So if you just print it out, then you see in red you get the type of the node is given to you. So you've got the PH data node up there, the composite node, and IO is then PH IO data node. That was just too long, so it's called just IO. And for IO objects, since they inherit from TObject, we can actually print out the base class, which is something you will need later on if you want to access the data. So if you look down on the lower right, if you print out the node tree, you get all the information you need when you want to write code which accesses these objects. One little caveat: once you put something on the node tree, you lose ownership. So please don't delete it. Fun4all will do that. If you delete it and Fun4all deletes it, you get a segfault at the end. Deleting of nodes is not supported. I don't see any good reason for that. If you give me a good reason, then I'll work on that. Now, coming to your analysis module. Again, everything is modular, and if you really think about it, for an analysis, you don't need that many entry points. So what we have a base class for the analysis, and that basically gives you the methods which are called by Fun4all. And again, it's a base class. If you don't implement them, it's perfectly fine. So what do you have? There's an init method that's called once when you register your module with the Fun4all server. You saw in the coding in the macro example, at some point you say server register subsystem and then your subsystem. So this is when the init method is called. We have an init run method. This is more important for when you take real data, where typically data is taken in runs. And since run normally means you have new calibrations, so you basically want to be called for the beginning of a run. So it's whenever data from a new run is encountered, this thing is called. Process event, that's called for every event. Reset event, in case you have internal things you want to reset after an event is processed, so you get called there. End run is called when a run has ended. And the argument is the run number, just in case you have something you need to do then. And then we have an end method, which basically gets called, before we quit. So this is the place where you, save your histograms and do stuff, before you go away. As you can see, the argument is always the node tree. So this helps you then, basically gives you access to, our basically to all these global objects. You can, as I pointed out, we can have multiple node trees, and you can tell fun4all to register your module with the given node tree. It doesn't have to be by default. You get the default node tree. If you give it another node as a second argument, you basically use that node tree. So now, how do you actually navigate this? Again, there are code examples later on. So what you need to know is the name of the node and the class of the object you want. And now, if you go back to the printout, you have the node name, and it tells you which class is stored in there. And down here, you see this is not just a snippet of analysis code. It's the process event method. You get handed down the top node. And we have a templated class. It's called get class. And basically, what you do, you say find node get class. The class type. So that's the PHT for hit container. That's our generic the G4 hits. The argument is the top node, and then you give it as a second argument the name of the node, and then it goes off and finds that object for you. And if it is of the correct type, you see down here is the protection with the G. You check for a null pointer. If it finds it, you basically get the object handed over here, and you can work with it. One little caveat is this get class returns the first node of a given name. Now, if you have multiple identically named nodes, then you have to do a different search. Can be done, but the recommendation is just don't have duplicate. Don't use identical names. You're basically making yourself unhappy. Okay, now let's go to our first example. A simple detector with a hard-coded geometry. Yeah. So let me go back to my EIC root directory. And source again my SVN setup. When you source the EIC setup script, you basically wipe out your previous environment. So all the settings I had here for the root include path and all that go away. So you're basically starting with a pristine environment. Okay, let me clone my example detector. And this time I'm not going to forget to go into the subdirectory. Go into my build directory, and just like before, I'm going to build this into the same installation directory. As I pointed out, you want to have one install directory. Makes your life easier. The setup local script supports multiple install directories, but again, it's you're probably going to make yourself unhappy if you try that at some point. Right. Since I've reset my environment up here, so I need to source the setup local again. Then let me go to the macros directory. And let's have a quick look at the macro I'm going to run. So again, it takes the number of events as input. This time I'm setting the random number seed, just so that I know how the first event looks like, because now it's reproducible, and whatever I'm doing, I've tried it before and I know exactly how the event's going to look like. That's nice. Very good for tutorials. I have my particle gun again. This time I'm just shooting one pi minus into this thing. So what I'm doing with this setting with the vertex, I'm basically putting it right into my detector. Here's again the PhD for Rico. I'm making a new one. Again, no field. I don't want the geometry. Here I'm making my example subsystem, yeah, and I register with G4 Rico. That is something we'll get to. So here's some code. It's some analysis code. So what it will do, it will basically take the stored 4 hits and put them into an n tuple. Yeah? So this is a new it's a new reconstruction module. This is a parameter. This is a method from the G4 hit n tuple class. So I'm just adding this node to it, and then I register the hits class, the hits object with fun4all. And down here again, it's a dummy manager. So I'm just running again an empty event loop. Let's do this. So just to show you what's inside these display function display, I'm always loading. So there's a method or function in there which basically calls the Qt GUI from Geom4. So basically, what it needs to do is, again, you get a pointer to the fun4all server. No, it has to get a pointer to our Geom4 implementation, to this PhD for Rico. What I need to execute is the init run method of it. So it basically puts everything to Geom4. So this is where everything is initialized, and then I tell it to start the GUI. Yeah? So. Oh, there we are. Yep. It's a block with a hole in it. Now, let's... Okay, let's run one of these events, the pions. Okay. That's educational, right? Yeah. So, yes, we can put things in there, and we can produce some kind of event displays, but it's actually kind of sad. Yeah? So you really want to do more than that. So, no, it's not different from Yaroslav's example. Yeah? Okay, now what can we do with our analysis code? So let's do a Giantino scan of this thing. Yeah? You can imagine, this thing sits at the center, but often you have rotation, translations. How do you actually verify that your detector position is where you think it should be? You saw in the Qt GUI, yes, you can move this thing around, but you have no idea how big it is and in what place it actually is. You can put axes in there, but the really fine details, is there overlap with something else? You really can't tell. So for this, for people who don't know what a Giantino is, it's an artificial particle. It's non-interacting, made by Geom. Geom4 introduced now also charged Giantinos, so they basically don't interact but have charge. And yeah, typically April 1st there's a discovery announcement on some CERN web page. Yeah. So. And this is when you hit the X for your no machine client. rather than the X of the Geant 4 GUI. Oh, this time I'm going to hit the right one. And as you can see, when you X this out, you get the prompt back to fun4all. So let me get to the example 1A now. We've sourced these two things, so let's skip that. Just start up root. Let's see what this Giantino macro does. So what it does, the only difference to the previous one is that it uses now this particle generator, puts a Giantino in there, puts the vertex kind of right into the center of the hole, and then just sprays particle around along some eta and eta range and phi range. Okay, momentum for Giantinos is irrelevant, so we'll just set it at 1. And okay, it starts at there's no no smearing of the vertex, register it and then do all the rest. So luckily Giantinos are really fast, so we can track 10,000 of them rather quickly. Okay. And as you can see, here's now a file hit untable.root. So this is where our hits are in. So let's open this with root. And what this n-tuple contains, among other things, is the coordinates of these G4 hits. So x1, y1, z1 is the exit coordinate. x0, y0, z0 is the entry coordinate. I'm plotting the exit coordinates first because they sit on the outside of the volume. If you do it the other way around, then you don't see the outside of it. Yeah. So that's the outside. You can see, big hole. Now let me put the entrance hits at the same, in red. So here you can see you've got the hole on the inside, and here's the outside of the device. Oh. The scale here is in centimeters, so you actually get an idea how big this thing is, just in case you messed up centimeters and kilometers or something. Yeah. Okay, let's continue with that. So basically what we plotted was the entry hits in red and the exit hit on the outside. And since it's Giantinos, the only basically the only time when a hit or a Giant 4 step ends is if it leaves the volume. So these Giantino scans are very easy tools to figure out where your volumes are, and if they even might overlap. So now what I also said is that you can save and read back snapshots. So let's do this here. We can let's look at example 2b. No, 1b, sorry. Yeah. Okay, let's see. So what are we actually doing right now? So the macro, as you notice when you compare them, is identical, except for this line down here. Here, we actually make ourselves an output manager. So it's a DST output manager, so writes out DSTs. Give it the name of this, and we just register the output manager with fun4all, and fun4all creates the output file with all the nodes saved in basically with a node tree saved in there. So you've got the structure, and you've got the hole in the box, the data content of it, and also, okay, we don't use it, but you also save the field configuration. Yeah? So now let's read this thing back. Yeah? The good thing is if you read from a file, you can give it the number of events equals 0. It will basically run until the file is exhausted. So how does this read DST look like? This is the same code you had in it's the same code you had in the previous macro when we basically did the hits and tuple write from the data, and use a DST input manager now, and give it the name of the file, you register it, and you run over it. Yeah. And you see there's a new file. Yeah, and lo and behold, looks the same. So what this example shows is, again, fun4all basically provides you with an analysis chain. This is kind of the model how this works. You can save at any point, you can read back, and your code doesn't change. No matter if you start with a simulation or with reading from a DST. Yeah. Yeah. As you can see, this stays. Yeah. It's the same for all the macros. All right. Now let's get to a more interesting example for everybody who's tasked with creating a vertex detector or silicon or TPC or something. The first question for any tracking design, in the first stage is, what is the momentum resolution? What do you think it can do? Yeah? And for secondaries, all that, what's the distance of closest approach? How well does it work? And naturally, since we are all students, the supervisor then the next question is always, can you do better? Yeah. What do you do? Can you modify things? And the last question is, this is really expensive. Can you do with fewer layers? Can you, redesign? So what we have is a full, for simulation using a full Kalman filter reconstruction and vertexing. So what you do, you put a detector together from simple shapes in a root macro. So these are the cylinders I pointed out. So that's what we're going to see now. Then you pick your particle and a couple of energies. You tell this tracking the error on the hits. So basic granularity of your detector, and you run. And then, wash, rinse, repeat, until you or your boss, likes the result. And then you can go into more detailed simulations. So what we're going to use is this cylinder setup. It's 6 layers of silicon. On the right, you find the radii and the thickness, so in centimeters. This is actually an old silicon design from us, and it's already been optimized. So we're going to change a few things, and it will only make it worse. Yeah? So, and what we're doing here for this for this test is we're using 4GeV positrons. Okay, let's go. Go back to our root directory. And okay, in order to make this shorter, you've seen the detector. I think you can trust me that I can display it. It'll look the same. So now let's actually go into the, but we still need to check out the code. Okay, reset our environment again. Start from scratch, always a good thing. Now, as you can see, this is part of the tutorials I mentioned on one of the first slides. Yeah. And this time, we don't even have to compile any code. Yeah? So it's really just a macro which calls pre-existing modules. Let's just have a quick look what's in there. I hope I cleaned it up. Yeah. Okay, so you should, kind of recognize these things. So we have our particle generator. E+, okay, that's a Jean positron. Starting at 0, 0, 0. We give it a very narrow eta range because we want to have it basically around mid rapidity. 4GeV as the momentum. And okay, we do this between 0 and 90 degree. It really doesn't matter since this thing is azimuthally symmetric. Okay, we register the particle generator with fun4all. Okay, now we have call again our PhD4Rico, basically set up the simulation. This time we give it a 1.5 Tesla solenoidal field, so weaker, stronger, whatever you want. This is just an array with the thicknesses of the silicons I mentioned on the previous slide. The radius, the length is okay. We basically have we can basically set it to a certain eta coverage if we want to. Yeah, but for this test, that's irrelevant. And then we use one of our generically implemented subsystems. So it's a cylinder. And what you basically give it, okay, first you make a new one. It needs a name and a layer number. So we start, silicons come in layers. So we set the radius to the number up there. We tell it's silicon, and we give it the thickness. And then we tell it it's an active detector, so we actually want to save the hits. If we don't call it active, then Geom4 will propagate the particles through it, but the stepping action is not going to be called. So you will not be able to get any hits out of it. And then we have a construct that we can, put multiple of these. This is a loop. You made 6 of these. You basically want to access them under one name in the end. So we basically call the super detector. So they will show up as SVTX. And then you have to give it a length. You register it with G4Rico. And that's it for the silicon detector. We have another feature. We call this. It's a black hole. It swallows everything. It's very useful. Normally, if you have a colorimeter, for example, you want to see how much comes out. How big is the leakage of a colorimeter? You basically put one of these ones behind. It swallows everything and basically tells you it basically dumps the energy of the incoming particles. It doesn't propagate them any further. And here we put a black hole around it, so you don't have any loopers basically going out to long distances and coming back in the solenoidal field. So basically not confuse our tracking. We register the truth subsystem, so the truth information is being kept, and then we register G4Rico with fun4all. The next step over here, that's our fast Kalman filter. So it's fast pattern recognition with a full Kalman filter. it uses the truth information to basically find the hit, so there's no track finding involved in here. It uses the actual hits, but then performs a full Kalman filter on that using the geometry we set up with the silicons. Down here we have we give it the resolution, so azimuth, radial, and Z resolution. I think these are like 30. What's up? That's 30 microns, 300 microns. No, we don't have any noise in here. We assume 100% efficiency. Okay, again, it's an analysis chain. So up here, the simulation is basically set up. So this is now analyzing the simulation output. So okay, we register the Kalman filter with fun4all. Okay, that basically just puts another node on the node tree. It puts, again, like every other module, puts information on the node tree. Then we have the evaluator here, which then takes the information from the node tree and dumps the output into, analyzes, dumps the output into an n tuple. And again, you have to register it with fun4all. And again, since it's a particle generator, we use a dummy input manager. We're not going to write anything out here. With these backslashes, you can actually you can run root like with a full command line. You don't have to basically start root and then call a macro. And what we do, we run over 1,000 events. Okay, and here you can see a snapshot of the node tree. These are the hits on the silicons. That's the output from the Kalman filter. So that's, we call it track map. We have the hits from the black hole. So we are not going to look at that, and we have the truth information. Under the runwise information, we have the geometry of the silicon. So we can use it later on in the tracking. These are actually the parameters from the silicon. So what material, the parameters of cylinder, what material, what's the radius, and so on and so forth. This is then the geometry, which is then later used by the tracking. We do the same thing for the black hole. The black hole itself is a cylinder, so it does the same stuff. And then we have we save everything as a TGeo object as well, which again, that's then what's finally being used by the Kalman filter. So we have the T geometry over here, and anything under the power node is not being saved. Okay, stuff is done. And we have a new file here, so let's open that. And not forget to double click. I'm just showing a few entries over here so that we save quite a lot of information there. But now, since we are interested in the momentum resolution or PT resolution, sorry. So let's just plot the reconstructed momentum over the input, reconstructed PT over the input PT. And you see, you've got small stuff down here when things loop or decay. So let's restrict this a bit. So we get a clearer picture. Yeah. And you can see we basically we lose a bit of since they go through material. So yes, they lose a bit of momentum. But it's not nicely centered around the mean, and okay, here's the RMS, so it basically is a measure for your momentum resolution. Now let's have a look at the distance to closest approach. So how well do we point back to the vertex? And as you can see, again, there are a few which really don't point back to the vertex well. Let's restrict this again a bit. So this is basically how well they, how well they're basically tracked back to the vertex in this configuration. Okay, in the interest of time, I'm not going to go through all the examples. So now you can start modifying this momentum macro. And here's basically a selection of things when I play around with it. So again, it's all positrons at 4 GeV at mid rapidity. On the left side, you find the nominal, basically what's in the macro right now, the plots you've just seen. Now let me just make the silicon 10 times thicker. And what you see immediately is the momentum resolution naturally goes down the drain. But you also see the buildup of this radiative tail to the front. So you can actually, again, for electrons and positrons, if you want to measure epsilons or so, that's what you need. If I play around with the radius, let's just make this thing a lot thinner. So just take using only half the radii for every layer. Again, you see that has a pretty bad impact on the momentum resolution, and also on the DCA. So these are playing around with the silicon itself. Now I can go into the Kalman filter and I can mess up that resolution. So basically take a tenth of the resolution they have, or by a factor of 10 worse in granularity. And again, you can see what kind of impact this has on the momentum resolution and on the distance to closest approach. Yeah. Now, if you want to do a real momentum resolution plot, like on the right side, as I said, wash, rinse, repeat. So what we did just now was basically 4 GeV was basically one of these guys at, okay, this is a measurement at forward rapidity, so you make one of them. As you can imagine, bottom line, this prospect is meant to motivate you to learn about programming loops and running batch jobs, because you don't want to run this stuff by hand. Again, these are root macros. In principle, you can actually implement this inside a root macro and loop over that. That's possible. And all of that is already exists out of the box. You don't have to you don't have to invent anything. You don't have to write any code. You can basically just use this thing. So now let's come to our final example. Now you have some detector and you want to add a detector to an existing setup. Yeah. So this is now the third example. We go back to my root directory. Again, let's reset our environment. And add the installed code. So that's Yaroslav's module plus our first example code there. Clone the macros and basically go down to the macro directory. So the way our macros in this repository, so this contains the descriptions of our full-blown EIC detector, of S-Phoenix, and also S-Phoenix instrumented with forward detectors. The deal for us is that we promise that we keep these macros functional. So if there are changes in them, we basically always make sure that these things work. It's set up modular. So these are the top steering macros. They in turn you find this G4 setup macro. So there's one for the EIC detector, FS Phoenix and S Phoenix. And they then out of these G4 macros basically assemble the whole detector. So for example, the beam pipe, as you might imagine, that's simple. This is just a cylinder. Again, we have a generic cylinder. We just say, okay, it's a cylinder made out of beryllium. The inside is G4 galactic, so basic vacuum. So this is basically what puts our beam pipe together. More complicated detectors. Let me see. Will look like this, where there's a dedicated class. So that's now our inner hadronic calorimeter. And the hadronic calorimeter has a bunch of parameters you can change. So you would basically, if you want to modify things, you want to play around, you change any of these parameters, and then you can just run it. In the end, if you want to add your own detector, you would probably create one of these macros. And what we're going to do now, we're not going to use the QT interface, because for more complicated detectors, it basically takes forever. It's easy to wait an hour for the display to come up, so you don't want that. And even this is going to take a while, so let's go back to the to what you're going to see. Yeah. So what you see here is our full-blown EIC detector. So it has the bar magnet, the outer hadronic calorimeter from S Phoenix, the inner hadronic calorimeter from S Phoenix. It does have it does have an electromagnetic calorimeter. It's not the SPECAL used in S Phoenix, because we're still working on the length of it, so that's more parameterization of it. That's a simple setup. It has the Dirk inside. It has forward gems. It has silicon layers in here. It has a TPC. It has a ridge detector, few more gems, forward ecal, forward HCal. I think one of these ones is also an ecal. So this is the design study we did here for an EIC detector. Wow. Oh, hey. So, okay. Let's go back to one of the first slides. So when I added Yaroslav's detector to the existing EIC detector, basically, the only thing you need to do here is you open the setup macro, the setup EIC detector macro, and the only thing you need to do, where's my mouse? The only thing you need to do is you have to include, again, Kling wants includes, so you have to include his basically his detector in the macro. Then you have to load its library in the root macro, and then let's say after line 310, it's basically before the truth subsystem, you register his luminosity monitor with G4Rico, and you get this here immediately. So this is basically how you can, as I said, you can mix and match detectors. Yeah. So this is basically how you add a new detector into the system. The huge advantage is you're not modifying any central code doing so, which is then basically the problem I see when you have to edit centralized code is that if that centralized code changes for some reason, oh yeah, no, we need to implement something else. You have to propagate this into every single person's code. While in this environment, you basically change it in the central code, and people still can use their macros to add these things. Yeah. So what we have is that there's no centralized code where people step on each other's toes, or where you have hostile interferences between detectors. That's basically, yeah, I think. Yeah. So that's basically it. Let's see if the detector is finished in the meantime. Nope, it's still working. Again, that's something you want a fast graphics card, and you need patience. But you need the same patience for when you do anything on the Jean command line. Okay, let me wrap this up. So help, how to get help. We start with the documentation. So that was the links sent around. So this is where you find the example codes. We use MetaMost as chat. That's basically an open source Slack. It's a public channel. RCF accounts can subscribe, without any permission or so. Non-BNL accounts would need an invite. So you basically have to send us a mail, and we'll send you an invite, and you can access that thing. The advantage over Slack is that we preserve the history. Slack, at least the free version, you basically after whatever 10,000 messages, you lose the history, or after a year or something. So we can keep this over here. We are using this. We started to use it about a month ago. We have very good experience with it, so it works well for us. Last resort, just send me or Jin an email. We'll get back to you as soon as possible. Our response time is normally less than an hour. Let me get to the final remarks. So this was just kind of a small selection of our capabilities. fun4all was used to simulate and design a new collider detector. So what you saw there, the EIC setup, or S Phoenix, is being built right now, and we simulated and designed it with fun4all, with what you saw. It was used for published EIC detector concepts, so it's certainly capable to design and simulate EIC detectors. In terms of synergy, in terms of collaborating, there's a lot of synergy. So it's a collaboration with an existing experiment, which ensures long-term support. What my collaborators would say, like, no, we're not doing this anymore because I'm bored with it. Yeah, not an option. So this thing will stay around, and we have warm bodies to work on it. So we do huge improvements in our tracking code right now. I mean, you saw the heavy iron event. It's a lot more challenging than in the EIC, and the EIC will definitely benefit from whatever we are doing over here. So currently we're working on acts, and don't want to say we're almost there, but I guess like a couple of weeks, and we have got this running. We have a full-blown, we have regular track reconstruction already. So that's code which can be reused. Also, clustering for the colorimeters, for example. Additional benefit is you can read and reconstruct raw data, from RCDAC, which is commonly used in the ERD programs. In terms of how you organize things, EIC specific detectors. We have a GitHub organization EIC detector. They can basically go into a repository there. So they don't have to go into our system. They can live happily down there. We have an EIC CVMFS volume, which we keep in sync with the SPhoenix one. But again, additional third-party libraries, additional detectors, they can go in there and live happily. As a user, you can use your own repository, and you just link against fun4all in CVMFS. I mean, basically the examples I showed. You have your own detector, you have your own repository, and basically in the macro you just add yourself to fun4all. So again, there's no central code which needs to be managed when you want to add your detectors to it. In terms of distribution, so we decided to use CVMFS to distribute our packages and libraries and provide a singularity container to run this. That seems to be the most seems to be the best way forward, so we don't have to deal with operating system and compiler quirks on whatever zoo is out there. So what we have there should run on most platforms. We've run it in JLab. It will run on the OSG. So I haven't submitted an OSG job yet, but Singularity exists on the OSG and CVMFS, so shouldn't be a problem. And yeah, congratulations, you made it. And this is where I have to say something.
Yeah. At least I will say something. Thank you very much, Chris, for the fun4all tutorial. Are there any questions for Chris?
Everybody sound asleep?
I don't think that anyone is asleep. I think that this was very exciting, but it was a lot of information to process.
I have a question. Go ahead.
Yeah.
Oh, okay. So if we go back to slide 42, for example, if I want to so this is adding adding detectors to existing setup. If I want to modify an existing setup, say in this case, if I want to remove everything and only strictly look at the vertexing silicon side, I'm assuming it's the same idea.
Yeah.
Okay.
Oh, this is done in the meantime. Please quit this thing. So let's have a look at the EIC detector. Again, if you've got the ton of include files, just don't look at them. Don't make yourself unhappy. The way we've set these things up is that we have, switches at the beginning of the macro. And here you can find the detector setups. Well, tracking means it's the silicon plus the TPC. If you set this to false, there will not be any tracking detector, and you can put your own thing in there.
I see.
And so, I would probably also set the beam pipe to false. Again, if you will get help when this question arises. I know these macros they are a handful. I'm not trying to hit anybody there. They look kind of complicated and they are a bit messy. But in general, if you just want to turn off detectors, that's done here in the front. You can also, you see over here, the tower reconstruction. You can basically, also turn off reconstruction at any point if you want to. Yeah, so you basically I just want to have the 4 hits. You certainly don't want to run the evaluator and the tracking itself, the track finding. It takes a lot of time, and if you just want the hits, you basically adjust what the output at this level. And if you want to put something else in, then we have to go a bit deeper into the macros. But there was the setup macro, and this would be the place where you put your detector in. Yeah.
I see. Okay, thank you.
Are there any more questions?
So basically, you see, the way we do this in the macros, we basically provide, the macros, again, similar to everything else. So they have an init method that they initialize themselves, and yeah. So this is the simulation part. And if you then look into these G4 macros, then they also have a reconstruction part and all that, which then gets called somewhere else. But we try to keep, the subsystem specific implementations. They stay in their own macros. And these setup macros, they basically just loop over them and call, just all the pieces which are necessary.
Gotcha.
Are there any more questions for Chris? So the tutorial is being recorded, so you will be able to just see this again. And as Chris pointed out, there are ways to get in contact with him and the fun4all crew in order to get started and for more detailed questions. So thank you very much again, Chris, and then let us end today's tutorial.
Right. Sounds good.